Shannon's first theorem tells us that entropy of an alphabet may be interpreted as the average number of binary digits or binaries necessary to represent one symbol of that alphabet. Let us extend this interpretation to the a priori and a posteriori entropies which we studied in the earlier class in relationship to information channel. So, the information channel was denoted by this figure as shown here. A is the input alphabet, B is the output alphabet and P is the channel matrix. Before reception of the output symbol of the channel, we associate the a priori probabilities Pi with the input alphabet A. The average number of binaries necessary to represent a symbol from this alphabet is the entropy of the source, and that is H A. Now, if we receive a given symbol say B j, we associate the a posteriori probabilities P of A I given B j with the input alphabet. The average number of binaries necessary to represent a symbol from the alphabet A with this a posteriori statistics is entropy of A given B j. Since the output symbols occur with probabilities P B j, we might expect that the average number of binaries now average over B j necessary to represent an input symbol A I, if we are given an output symbol, is the average a posteriori entropy. So, what we expect that the average value should be P B H of A B. Now, for the sake of convenience, we will use the short notation for A's and B's whenever we are writing in terms of summation. Instead of B j, we will write B, and instead of A i's, we will just write A. So, this is the average number of binaries required to represent a symbol in input alphabet A, given that we have received an output symbol. Now, this result does not follow directly from the Shannon's first theorem. Shannon's first theorem deals only with coding for a source with a fixed set of source probabilities and not with coding for a source which selects a new set of probabilities after each output symbol. So, let us try to generalize Shannon's first theorem. In order to obtain such a generalization, we need to ask a question, that this question is similar to the one which we asked when we proved Shannon's first theorem, and the question is, what is the most efficient method of coding from a source? In this case, our source is the input alphabet A. Now, this time however, the statistics of the source we wish to change from symbol to symbol. Now, the pointer to which set of source statistics we have to use is provided by the output of the channel Bj. Now, since a compact code for one set of statistics will not in general be a compact code for another set of source statistics, we take advantage of our knowledge of Bj for each transmitted symbol to construct S binary codes. S corresponds to the size of the output alphabet. So, we will build S codes, one for each of the possible received symbols Bj. So, when the output of the channel is Bj, we use the jth binary code to encode the transmitted symbol Ai. So, let the words of our S code be as shown here. So, we have input symbol which are A1, A2 up to AR, and depending on what we receive, we will have that many number of codes. Since the output alphabet is of size S, we will have S code, and each of this code will have the code words with the lengths given as follows. So, for the code 1, we have length 11, L21. L21 corresponds to the length of the code word for the input symbol A2, and similarly LR1 corresponds to the code word length for the input symbol AR when I am using the code 1. So, similarly for code 2, we have L12, L22 and finally LR2, and for code S we will have L1S, L2S, LRS. So, we have S codes corresponding to the input alphabet. Now, we require that each of these codes to be instantaneous. So, we may apply the Shannon's first theorem which we had studied earlier to each code separately, and we obtain that entropy of A given Bj will be always less than or equal to probability of Ai given Bj Lij averaged over input alphabet A, and this by definition we will call it as Lj. This is the average length for the jth code. Now, here we employ the conditional probabilities Pai Bj rather than the marginal probabilities Pai to calculate Lj, since the jth code is employed only when Bj is the received symbol. So, the average number of bits used for each member of the A alphabet when we encode in this fashion is obtained by averaging with respect to the received symbols Bj. So, if we multiply both the sides by probability of Bj and sum it over the output alphabet B, we will get the following relationship: H of A given Bj multiplied by probability Bj over B is less than or equal to A B probability of Ai Bj joint probability multiplied by Lij, and this by definition we will call it as the average number of bits per symbol from the A alphabet, average with respect to both the input and output symbols. This relationship is similar to what we had done earlier for a single source. Now, in order to show that the bound can be achieved, we next describe a specific coding procedure. So, when Bj is the output of a channel, we select Lij, the word length of the code word corresponding to the input Ai, as the unique integer satisfying Now, word length defined in this fashion satisfy the Kraft inequality for each j. The Lig therefore define S sets of word lengths acceptable as the word lengths of S instantaneous codes. Now, if you multiply this inequality on all the sides by probability of Ai Bj, which is equal to probability of Ai given Bj multiplied by probability Bj, then we get a relationship probability Bj probability of Ai given Bj log of probability of Ai given Bj less than or equal to Lij joint probability of Ai Bj less than probability of Bj multiplied by probability of Ai given Bj log of 1 by Pi given Bj plus probability of Ai Bj. And now, if we sum this equation over all members of the A and B alphabets, we will get the relationship as follows. This should be P Bj Bj, but for convenience we are just writing as B, it is clear from the context. So, now this equation is valid for any channel of the type we have considered. So, in particular it is valid for the nth extension of the original channel, and if we apply this relationship to the nth extension of the original channel, we will get the following relationship. Where ln bar is the average word length of a channel from the source A n, that is the nth extension of my original source A, or equivalently the average word length of n symbols from the original alphabet A. Now, each a posteriori entropy h of a n given beta can be written as the sum of n terms of the form h a given beta. So, this can be broken into n sum of this form. So, if we use this relationship, we can simplify this expression as now, this expression is the generalization of Shannon's first theorem, and this is very similar to what we had done earlier for a single source, where we had obtained h of s is less than or equal to where this was the entropy of the source S. This quantity is the average number of bits needed to encode a symbol from the input alphabet A if we already have the corresponding symbol from the output alphabet capital B. So, now let us look into this expression given by summation over alphabet B of probability B h of A given B. Now, we will define h of A given capital B as probability B of h A given B average over output alphabet B, which we can simplify as once again here we will not write the subscript i's and bj's just for the sake of convenience in notation. It is assumed that this A is ai and is summed over the input alphabet A, and similarly this B is bj and it is summed over the output alphabet capital B, and this can be simplified as this is double summation over input alphabet and output alphabet, but is indicated in short by just one sigma sign. This is equal to probability of A and B joint log of 1 of by probability of A given B. So, this quantity is by definition equal to h of A given B, and that simplifies to the expression shown here. Now, this h of A given B in literature is called the equivocation of A with respect to B, or sometime it is also called as channel equivocation. So, in terms of channel equivocation, we can write the generalized Shannon's first theorem as limit of n tending to infinity ln bar over n is equal to h of a given b. We had derived a similar relationship earlier while proving the Shannon's first theorem, but there is a major difference between this relationship and the relationship which we had obtained earlier. The difference is that in this case successive input symbols ai or blocks of input symbols are encoded using different codes corresponding to different output symbols bj or blocks of output symbols occurring. Now, even though each of the codes used is uniquely decodable, it is generally not true that a sequence of code words from a known sequence of a uniquely decodable code is uniquely decodable. So, in this case it is not sufficient therefore to select a set of uniquely decodable codes with word length satisfying this condition. Then another condition is that codes must be instantaneous. So, what it follows that the earlier relationship which we had derived, this relationship is valid to only instantaneous code, unlike the Shannon's first theorem which applies to all uniquely decodable code. Let us reconsider the information channel which we had studied earlier. The information channel consisting of our inputs and S outputs. So, we have A, we have B, the size of this is S and the size of this is R. Now, the inputs are selected according to the probability P A I for I equal to 1 to R. So, the entropy of the input alphabet can be calculated as P A log of 1 by P A. If you have an input probabilities and the forward probability is given by the channel matrix P in the form of probability B j given A I, we have seen yesterday that we can calculate the backward probabilities, that is probability A I given B j, and we can also calculate the joint probabilities P A I B j, and therefore, we can calculate the equivocation of a channel which is defined as h of A given B equal to B log of 1 by P of A given B. Now, by Shannon's first theorem, we need an average of H A bits to specify one input symbol A I, and by the generalization of the second of the Shannon's first theorem which we just saw, we need only on average H of A given B bits to specify one input symbol if we are allowed to observe the output symbol produced by that input. Now, what it follows that on the average observation of a single output symbol provides us with H A minus H of A given B bits of information. So, on the average, the observation of a single output symbol provides us with this many number of bits of information. So, on the average, the observation of single output symbol provides us with this bits of information, and this by definition is called as mutual information that is of A and B, or it is also known as the mutual information of the channel, and it is written as I of A H A minus H of A given B. So, this by definition is the mutual information. Another way to interpret is this, that before I observe the output symbol B j, the uncertainty of the event A was given by the entropy of the source. On observing B j or output symbol, the entropy on the average or the uncertainty about the input symbol is H of A given B. So, what it means, the difference of these two entropies should be the uncertainty resolved. So, I can interpret this as uncertainty resolved of the amount of information which I have received. So, now with this definition, let us develop some alternative ways of writing the mutual information. So, if you look at this expression, we can write it as A of P A log of 1 by P A minus double summation over A B probability of A B log of 1 by P A given B. This can be simplified as, this we can write as probability A B log of 1 by P A summed over input and output alphabet, because summation over B will give us the marginal probabilities P A, and probability A B log of 1 by probability A given B, and this can be simplified as probability of A B log of probability A given B over probability A. Now, since probability A I B j is equal to probability of A I given B j multiplied by probability B j, we can write, based on this, we can write this expression equal to probability A B log of probability B So, mutual information of the channel or the mutual information of A and B is given by this expression. So, if we have the nth extension of a channel, we will find that mutual information can be shown to be equal to n times I of mutual information between A and B. So, we have shown that the mutual information is equal to the average number of bits necessary to specify an input symbol before receiving an output symbol less the average number of bits necessary to specify an input symbol after receiving an output symbol, that is, can be written as shown by this expression. Now, an immediate question that arises is that what about the sign of H A minus H of A given B? Can mutual information be negative? Now, we have seen yesterday with the help of an example that H A minus H of A given B j may be negative. What it means that entropy of the input alphabet may be greater after reception of a particular output symbol B j, but the mutual information is just the average over all output symbols of H A minus H A given B j. So, it is an average of this quantity over all output symbols. Now, the question is, can this average be negative? So, to answer this question, let us write A B as given by this expression Now, we have seen the relationship that if I have two random variables or two set of, now we have seen that if we have two set of probabilities xi and yi's, then this relationship which we had derived earlier is valid. So, using this relationship, we can immediately see that I of A B is greater than or equal to 0, where xi's correspond to probability of A B and yi corresponds to P A multiplied by P B. So, and this will be, and this inequality will be equal if and only if yi is equal to xi, that is probability of ai bj is equal to probability ai multiplied by probability bj for all I j. Now, what it says that the average information received through a channel is always non-negative. We cannot lose information on the average by observing the output of a channel. Further, the only condition under which the average information is 0 occurs when the input and the output symbols are statistically independent, which will happen when this condition is satisfied. Another important property of the mutual information may be seen by inspection of this expression. This expression which may take as a definition of I A B is symmetric in the two random variables A I and B j. So, interchanging the roles of the input and output symbol leaves I of A B unchanged. So, we may therefore write I of A semicolon B is equal to, therefore, we may write I of A B is equal to I of B A. So, carrying this argument even further, we may write I A B is equal to H B minus H of B given A, because I A B is equal to H of A minus H of A given B. So, similarly, I B A is equal to H B minus H of B given A, where H B is by definition equal to entropy of the output alphabet. And H of B given A is equal to joint probability of A B log of 1 by probability of B given A summed over input and output alphabets. Now, this is called the equivocation of B with respect to A. Now, in addition to the entropies H A and in addition to the entropies H A and H B, it is possible to define a joint entropy which measures the uncertainty of the joint event A I B j, and that will be given as H of A B is equal to summation of probability A B log of 1 by probability A B summed over input alphabet, output alphabet. Now, the relationship of H A B to H A and H B can be easily derived as follows. Probability A B log of 1 by probability A probability B. So, this by definition is equal to negative of mutual information of A and B, and this can be split into two terms as follows. Plus log of 1 by P B, and this can be simplified as mutual information plus entropy of the input alphabet plus the entropy of the output alphabet. So, this relationship can be easily depicted in the Venn diagram form as follows. This circle corresponds to entropy of the output alphabet. This circle corresponds to the entropy of the input alphabet. This intersection corresponds to mutual information of A and B. This portion out here without the shaded portion is h of b given A, and similarly this portion out here is h of A given B, and this total is h of A B. So, the entropy of A is represented by the circle on the left and the entropy of B is by the circle on the right. The overlap between the two circles is the mutual information. So, the remaining portion of H A and H B represent the equivocation H A given B and H of B given A respectively, and the joint entropy, that is H of A B, is the sum of H A H B except for the fact that the overlap is included twice. So, we get, looking at this Venn diagram, H of A B is equal to H A plus H B minus A of I of A B. Now, from this Venn diagram, it is very clear that H of A B is equal to H A plus this portion. So, that is H of B given A, and similarly H of A B is equal to H B plus the remaining portion out here, that is H of A given B. It is, physical interpretation of this is very easy to see that the uncertainty of the joint event A and B is equal to the sum of uncertainty of B plus the uncertainty of the A given B has been observed, or it is also equal to the uncertainty of the event A plus the uncertainty of the event B given A has been observed. So, now our primary interest is in information channels. So, but it is important to know that A so let us compute the mutual information for a binary symmetric channel. The channel matrix of the binary symmetric channel is given as P bar P P P bar where p bar is equal to 1 minus p. Now, assume that probabilities of a 0 and 1 being transmitted are omega and omega bar respectively. So, we can write the mutual information for the binary symmetric channel, where the input and output alphabets consist of the binary symbols as h b minus h of b given a. This is equal to p minus probability of a, probability of b given a log of 1 by probability of b given a. This can be simplified as this quantity is equal to p log 1 by p plus p bar log 1 by p bar. So, this is equal to h of p minus p log 1 by p plus p bar log 1 by p bar. Now, the probability is that b j is equal to 0 and b j equal to 1 can be easily calculated, and it can be shown that this probabilities are omega p bar plus omega bar p, and probability of b j equal to 1 is equal to omega p plus omega bar p bar. From the channel diagram for the binary symmetric channel, it is very easy to show this relationship. Now, using this relationship, we can write the entropy for output alphabet, and if we write that, we get finally the mutual information as follows. Plus this is a mutual, this is the entropy for the output alphabet minus p log 1 p plus p bar log 1 by p bar, and this we can write in terms of the entropy function as omega p plus omega bar p bar minus h of. In the next class, we will provide a geometric interpretation of this relationship. We will also look at the definition of some information channels like noiseless channel and deterministic channels. We will study some interesting properties of entropy and mutual information as revealed by consideration of the cascades of two channels.